Okay, welcome everybody to today's AJS. Thank you for being here. And today with us we have Lorenzo Fabris. Lorenzo is a PhD student from the SISSA MATLAB group, and he will talk about his project with Fincantieri. And in particular, he will talk about the structural optimization of ship hulls. So Lorenzo, the stage is yours.
Okay, hello everybody. So this is the latest, is a presentation about the latest developments on this project, which itself is a third iteration of collaboration with Fincantieri on the optimization of cruise ship hulls. Okay, this is a joint work with Dr. Marco Tetzela and followed by Gianluigi Rozza and the senior naval engineers from the merchant ship business unit of Fincantieri here in Trieste. The goal of this sequence of projects, first name Iron, then Chaperons, now is the implementation of an automated computational pipeline for the optimization of the house. We use projection-based ROMs, so we start from high-fidelity simulations. We build the projection and the interpolation, and we optimize these surrogates with multi-objective optimization and single-objective optimization, refining the sampling of the high-fidelity configuration to drive the model, the ship mass to its minimum, and at this point we refine the problem formulation to achieve even better result. This constitutes a loop which streamlines the initial design phase. In the initial design phase, the designers have already finalized the geometry of the ship, and they have to make sure that it is a stable structure. This is done by simulating it against extreme wave conditions and checking the result on the structure according to classification society rules, so basically insurance companies for ships. The goal of the designer is to minimize the mass, while at the same time reducing the insurgence of failing phenomena of the steel, such as yellowing and buckling. Also, the deformation of the ship is kept under control, so the vertical deflection. And finally, the barycenter of the model is constrained so that the ship doesn't capsize. The decision variables that the designer control is the thickness of the steel plates composing the ship, How they do this? They basically divide the ship in its primary structural components. So the decks, the bulkheads, which are the longitudinal walls inside the ship, and the external shell, divided depending on the expectation of the work that of the structural work that's going to be done, and to each of these different elements, a different decision variable is assigned. So the thickness is controlled differently for the different components of the ship. The high-fidelity solutions are provided by MSc Nastran linear static elasticity, and the model which is studied is composed of 2D shells and 1D beam elements. The post-processing of the stress tensors of the elements gives the yielding and buckling of the different elements composing the ship. The displacement defines the deflection, while the BCG against the capsizing is in truth measured on the undeformed hull. So while MSc Nastran implements a joint-based optimization, it's pretty general. However, it does not support the particular buckling formulation which is required by the classification society. So we have to use black box optimization. And this, however, requires many query regime on the generation of different of the checking of different configurations. MSc Nastran is too slow even on an HPC cluster to do so. We employ indeed reduced order modeling. However, MSc Nastran is a commercial software closed source. We cannot use intrusive order modeling, and thus data-driven reduced order modeling is required. For this, indeed, we use POD. In this case, our input, well, the high fidelity configurations is constituted by the stress field, the stress tensor fields on the model elements. We split them by component, so 3D stress tensor has 6 relevant components. We assemble so a snapshot matrix of each, for example, sigma x, sigma y, and we decompose to obtain the basis, and the rest we throw away. The reduced coefficients of a particular snapshot of the stress tensor is obtained by projecting on the basis. The connection between the value of the parameters and the reduced coefficients is given by Gaussian process, is obtained through Gaussian process regression, in which basically we assume that each coefficient sampled by the parameters is a Gaussian process with some mean and covariance metrics. We employ here just the squared exponential kernel plus a term for the epistemic uncertainty and automatic relevance determination. The prediction is obtained by conditioning on the high fidelity, well, actually high fidelity truncated coefficients. So in the online phase, we query the GPR. We have 2 log conditions, 6 stress components, times the truncation rank produced coefficients. The predictions are then expanded to their original dimension. The stress tensor are reassembled so that the post-process step is the same that Fincantieri would use on the results from Nastran. And there are 7 yielding criteria, one for each stress component plus the von Mises, and 11 buckling usage factors, which determine the buckling, and these are given by the classification society. And this online phase is extremely efficient due to every operation being done in either Toscini matrix vector products or vectorized functions, such as the case for the yielding and buckling criteria. And so the speed up is in the order of 800 times compared to the MSc Nastran result. The truncation rank, which is a very important component of the capability of the POD, in our case is always close to the number of the parameters. So for example, this is the singular values decay for a model with 5 parameters, and from the experience matured on this project, 6 is the right truncation rank, because it is validated on the actually on the actual interesting outputs. The number of yielded elements and buckled elements. If we were just interested in the accuracy of the prediction, a much higher rank would be required. But instead, due to these being essentially classification problems, a small rank of the reduction enables us to achieve high accuracy with very low effort. So with these surrogates, we started the optimization. The multi-objective optimization is characterized by the fact that different quantities of interest have no direct mean of confronting each other. Basically, Fincantieri is interested in minimizing all of the mass, the cost, the deflection, the number of yielded and buckled elements. And so it's not possible to minimize both mass and buckling because they go one against the other. And so rather we are interested in finding the configuration that have the best trade-off between each of the QIs. The set of the configuration which offer the best trade-off is called the Pareto frontier, and the non-dominated solutions which compose this set are the points in the QI space which basically have no other element of the Pareto frontier which is better than them in every aspect, so in every component of the multi-objective vector. To do this, the established algorithm is based on a genetic algorithm, and it's called non-dominated sorting genetic algorithm. Here, the framework is that of the classic genetic algorithm, where, however, the fitness is given by the degree of domination. So the non-dominated sorting is the partitioning of the set of configuration in QI space with the selection of the Pareto frontier, the removal of it, again, selection, removal, selection on the remaining. This figure represents the first levels of the population, and these levels are used in the selection phase to prune the less fit individuals. There is a niching part, which basically is a downsampling of the population when it goes over the limit for the algorithm. Still, with a number of solutions selected by the multi-objective optimization, we need a criteria to give the solution to MSc Nastran to validate and enrich the sampling. And for this, we use an infill criterion based on the underlying Gaussian process regression. Basically, we are interested in enhancing the prediction ability of our surrogates on the entirety of the Pareto frontier. So every time we select a point, we want it to be empowering the prediction on all the rest of the points. So for this, we somehow aggregate by taking the sum as a first implementation, the covariances of the different load condition, number of load condition times number of stress tensor components times number of truncation rank. And we build an aggregation of the covariance between the low fidelity and between the low fidelity and high fidelity elements. We use we estimate an increment on, let's say, relevance of on the low fidelity elements given by the choice of the if element and its addition to the high fidelity partition. On this delta, we take the maximum, and this is the effect on the well, aggregated matrices, but we can see that this approach also maintains a decent, let's say, conditioning of the covariance matrix inside the GPR, which is essential for the online phase predictions. This is an evolution of the Pareto frontier is in hexadimensional, and these are just the projection and let's say the reduction in 2D, but we can see that as the number of infill executions goes up, also the frontier stabilizes. We use multi-objective optimization to get a global understanding of the capabilities of our model, but since we are ultimately interested in minimizing the mass, we also use a single objective optimization implemented with Bayesian optimization. So here again, we use a GPR, however, of our objective function, and the GPR gives us both a mean and prediction, but also a variance, so a degree of uncertainty on its prediction. By exploiting these uncertainty, the quantification of this uncertainty, it is possible to balance exploitation and exploration of the configuration, which then grow the sampling of the online GPR inside the Bayesian optimization. And finally, once the computational budget is exhausted, the best performing configurations according to the surrogate are sent to Nostrum for validation. This is an example of different acquisition functions. They have different capabilities in exploring or exploiting, essentially expected improvement and also the negative lower bound, lower confidence bound are they try to be optimistic in the presence of uncertainty, while probability of improvement tries to exploit the domain near known optima. At the implementation level, however, there are a number of refinements on the simple mass objective functions. First of all, our implementation, our actual objective function is given by the fixed mass. These are the thicknesses multiplied by the linear densities of our parameters, and bar is the mass of a secondary stiffener, which is basically the correction of buckling phenomena. So B is the number of buckled elements, plus, and this, let's say, is the physical mass, plus we have a penalty term which punishes a configuration according to its number of yielded, buckled, but also deflection scores. Y crit and B crit are the thresholds for a tolerable amount of yielded and buckled elements. So this is called quadratic penalization. And this function f is optimized can be optimized thanks to its GPR surrogate. We use LBFGS. The infill criterion is indeed taking the tree, actually best configuration. But it wouldn't work as good as it does without some more constraints. In particular, we take a linear constraint with the current incumbent solution to reduce the number of configurations, because we have a discrete domain that still need to be checked by the optimization. And also the VCG is able to express a linear inequality to reduce the search space. As an additional heuristic, the switching of acquisition function on the incumbent plateaus, so when no better solution is being found by the vanilla, by the current acquisition function, also gives a very good result. The repair, duplicate, or duplicated infeasible configuration is due to the internal rounding used by the framework we use, Mockito, by the way. And finally, when Bayesian optimization is not able to neither explore or exploit a new configuration, we apply a direct search. So thanks to the efficiency of the surrogates, we are able to quickly iterate over a large number of configuration, and we simply use a principled exploration near the incumbent. This is an example of single objective optimization. It is expressed with the gap on the lower bound for the mass of the parameters. So it has basically the buckled element, the mass of the buckled elements plus the penalty term plus whatever value for each parameter you are above the minimum. So Bayesian optimization is usually able to quickly dive, but then flattens out. In this case, we see that the infill of this configuration doesn't work as good as the GPR faults, so we start a bit higher. Then, after a Bayesian optimization is flat for all the iterations, we switch to the more principled, let's say, direct method. Once we achieve the optimum that neither multi-objective, neither single objective are able to refine, we reformulate the problem. So in this case, since our parameters are defined on groups of elements, we study how these elements respond to parameters change. For example, this is the internal bulkhead of the ship, and we can see that as the value for the thickness grows, a very large number of elements are not buckled. So in blue, it is, let's say, sane element. In yellow are the buckled elements. And if the optimizer was able to leave all the blue elements, all the elements that are blue from 6 millimeters on, and just use more steel for the upper right corner, it would achieve a lower final mass. So we want to find a clustering of elements inside of each original parameterized section. A simplifying element is that the MSc Nastran elements are in the physical world part of a same steel plate. So the model is actually divided in steel plates, and we call patches them in this context, and we can just optimize each patch. The assumption that we can use to optimize the patches is that the response of a patch to the change in parameter only depend on its own thickness. This enables to study the group of patches of each parameter separately, and if we are able to optimize the patches of a parameterized section to minimize the mass, the clustering will be given just by grouping the thickness of the patches. We use an integer linear program where x is the assignment of patch P to thickness T. This is just the physical mass of the patch, the physical mass of the buckled elements and their secondary stiffener, and a penalty similar, let's say, to the original quadratic penalty of Bayesian optimization, but here it is inside the summation. This is much more punishing of the failure of elements. The rest are just the constraints where, of course, a patch can be assigned only one thickness, and this variable ut basically counts the number of different parameter values that can be used in these parameters. So this program can generate 2, 3, 4 clusters and evaluate the result. Also, for example, the VCG can be embedded as a constraint to maintain feasibility of these, let's say, local refinement. This is an example of the application of this clustering. So in blue, it is represented the ratio of buckled elements for each patch. Each line is a patch, and the values of the parameter as they grow, the ratio of buckled elements diminishes, and the clustering as selected as assigned thickness 6 to the majority of the elements, while thickness 9 is used for the, let's say, upper left corner. These 3 patches which have remained blue did so because even if they were assigned an higher thickness, they would still be basically totally buckled, and so the optimization decided not to. So the entire procedure exploits the ROM, performs the clustering on the responses obtained by our surrogates. The selection of the optimal parameterization can be can be done with another integer linear program to, for example, choose between multiple parameterization for the same original parameter. At this point, the the procedure can just update all the metadata of the old high fidelity configuration, and the new parameters need still to be sampled to obtain, well, to extract the information of the different values inside the same original parameterized group. So as for the results, we first used simplified midship section. This is basically a quarter of the central part of a ship, 75,000 elements. The time for an online query is 0.15 seconds. We applied 3 different, let's say, threads of refinement. So the first optimizes, doubles the number of parameters, optimizes, etc. The second one, in one shot, passes from the basic parameterization to the limit on parameters we put. And the final is actually a parameterization given by the human designers with the maximum number of parameters. So this is the effect of the parameterization on the multi-objective optimization. So the base model is much more, let's say, has a much lower hypervolume inside the thresholds for the feasibility of the configuration. Compared to the 10 parameters and 17 parameters, the gain in capability of the model in the optimization is really conspicuous. But even more, as for what concerns the yielding and the buckling of the elements, the refinement is able to achieve much lower mass, okay, given the same threshold on the other quantities of interest. This is a comparison of the high fidelity incumbent as the number of optimizations in field validation grows. The base model, the reparameterization is able to achieve the lower, with lower values much faster than the designer provided parameterization, and also with half the parameters, the final performances are very close. From 17 parameters onward, we could have we could have reparameterized from 17 to 20, but the gain of the 17 parameter was so low that we decided not to. Indeed, the 17 parameter model is just slightly better than the other final results. And something to note, however, is that the constraint on buckled elements is the one that, let's say, is the most strict, but the one-shot parameterization still manages to come close to the best with a much lower number. So the designer have space to work in this optimum. We also tested on an actual commercial project. The ship is still being designed and has about 500,000 elements, and the online query is alpha second. Well, the actual number are still confidential on yield of the buckled elements, but we performed the same flow of optimization. In this case, the gain due to reparameterization are much less pronounced, but still the increment in hypervolume behind the hexadimensional Pareto frontier is conspicuous. And as the number of parameters grows, the gain presents diminishing returns as usual. This is the high fidelity incumbent, and in this case, well, I didn't say before, but these long flat zones in the plot are due to the multi-objective optimization, because due to the infill criterion, the entire domain is being explored, and it's the best mass is not necessarily improved. However, with the adoption of parameterization, we see a very sharp drop in, and this is due to the solution of the integer linear program being added to the high fidelity sampling. In this case, the designer provided parameterization while being faster to optimize does not is no match for the reparameterized configurations. And this is the final result. These are the final results. The 14 parameters of the incremental parameterization obtains the best mass. And here we can see, however, that the buckling constraint is exploited totally by all optima, and so it was not well, it is acting as a bottleneck even for the one-shot parameterization. And these are some references apart from the well, the my latest work wasn't on the multi-objective and the reparameterization, but all the previous modules were implemented together with Marco. Well, by Marco in the first place, then refined in this work done in this paper, and the second and third are excellent references for optimization in general and Gaussian processes in particular. We used EasyRB for the model order reduction, and Kit for the Bayesian optimization, DF for the multi-objective code, and Python MIP for the integer linear program. That's it.
Thank you, Lorenzo, for the nice talk, and sorry for the technical issues. Are there any questions from people here in presence? Curiosities, comments?
So thanks a lot. I have a few curiosities. So one is in the GPR model that you used. Have you also experimented a bit, let's say, the robustness of your model with respect to like the length scale, like DL in the kernel?
I use automatic relevance determination as a black box. I didn't study it.
Because I know that sometimes, of course, it can be difficult to set up the, let's say, the parameters in the GPR regression in that setting, but yeah.
No, I don't remember the actual values, but I think they were the default, and
they work. Okay.
Yeah.
Another one is probably something that I missed. So if you can give some more insights on how you compute the So which is the criteria that you use to compute the number of bubble elements?
Okay, they are straight implementation of the specification of the dat nostre veritas. And well, I'm not an expert on the theory of that. They are basically tables, well, not really tables of functions. So if aspect ratio above some number, use this formula.
Okay.
Or use the
or just some criteria that they have, like, so if you have a threshold, then this value is greater than this.
Basically,
okay.
So they are composition of functions,
Okay.
and they are computed anyway on the stress tensor components, plus some metadata like the aspect ratio and type of steel, of course, and things like that.
Thanks a lot.
Are there other questions here in presence?
Just curiosity about the high-fidelity situations. Do you know which kind of model and utility relation we use for modeling the infrastructure?
It's just isotropic linear elasticity.
Linear elasticity.
Yeah, that's for sure. The plates, I've not been able to extract the actual equations that Nastran uses, but it is a thin plate theory. Yes.
Other questions? Are there any questions from online? If yes, just unmute yourself and ask. Okay, I don't see questions. So if not, let's thank again Lorenzo. And see you at the next analysis junior seminar.